All right, let's take a look at the questions from section 2.2. So now we're looking at the geometry of systems of first order equations. So we have a cooperating species model. So you could look at this as maybe two prey species or two predator species. Basically, any two species that compete over the same resources in the same environment. And there's some kind of weak interaction between them. So we're told to set beta equal to 1/2. So first thing I want to do is find the nullclines. So what is a nullcline? It's related to equilibrium. But basically an X nullcline is where basically dx dt will be equal to 0. A Y nullcline will be, well, dy dt is equal to 0. So we can go ahead and look at these different systems individually. So if dx dt equals 0, then what does that give me? That gives me x times 1 minus x plus beta, we're going to set as 1/2 xy equals 0. I think it would be easiest to isolate y and look at what happens here. So let's go ahead and do that. So 1/2 xy equals negative x times 1 minus x. We distribute, what do we get? Negative x plus x squared. So y equals x squared. Actually, let's do this first. Let's double everything. So xy equals 2x squared minus 2x, which means that y equals 2x squared minus 2x over x, which gives me what? So can I divide by x? Well, I don't want to divide by 0, but I think it's reasonable to assume that x is not going to be 0. Because if x is 0, then this species is extinct, and there's no real reason to study what goes on with this. So y equals 2x minus 2. So here's a nullcline for x. So y equals 2x minus 2. Under this condition, we will have not equilibrium, but we'll have the dx dt. The growth of species x is 0. Let's do something similar for dy dt. I would expect this to behave very much the same way, but let's make sure. So I'm gonna go ahead and distribute off the bat. So y minus y squared plus 1/2 xy equals 0. Let's double everything. So 2y minus 2y squared plus xy. I isolated y last time. Now I only have one instance of x. I'm going to isolate x. So for the same reason that I assumed that x could not be 0, I'm going to assume that y cannot be 0. I want to study this system assuming that there are populations of both of these things. So xy equals 0. Xy equals 2y squared minus 2y. So then y equals, no. X equals 2y minus 2 over, am I getting ahead of myself? I think I am. 2y squared minus 2y over y, which is equal to 2y minus 2. For the sake of, eventually I'm going to want to plot this. That's what step C is. So I'm going to go ahead and solve this for y. So what do I get here? I get that 2y equals x plus 2, or y equals 1/2 x plus 1. So here are my nullclines. If y equals 2x minus 2, and y equals 1/2 x plus 1. So the first is my x nullcline. The second is my y nullcline. So where does equilibrium happen? So for a single equation, I have equilibrium if that equation, if dx dt, for example, is equal to 0. If I want to know where a system is under equilibrium, then what I want to know is under what conditions are every equation equal to 0. So my nullclines will essentially help me do that, because my nullclines tell me where a single equation is equal to 0. Now I can basically set them equal to each other to figure out where they're both equal to 0. So it's going to be the intersection of these two straight lines. So y equals 2x minus 2, y equals 1/2 x plus 1. Let's go ahead and double everything again. So 4x minus 4 equals x plus 2. So then 3x equals 6. That gives me x equals 2. If x equals 2, then what does y equal? It doesn't matter which one of these I plug this back into. But let's make sure let's do both just to make sure it agrees. Y equals 2x minus 2. So 2 times 2 is 4, minus 2 is 2. Y equals 1/2 x. So 1/2 of 2 is 1, plus 1 is 2. So there's my equilibrium condition. X equals 2, y equals 2. So we found our nullclines, and the intersection of those nullclines told me the single equilibrium point I have for the system. Now I want to sketch the phase plane. So let's start with a rough sketch, but then I'm gonna lean on technology to do this for me. So phase plane essentially it serves the same purpose and conveys the same information as the phase line does. So it shows you where the equilibrium points are, and it shows you what the behavior is around those points. But on a phase line, I only have to worry about one dimension because I only have one variable. In a system of equations, I have two variables, or in this case, I have two variables. It could be more. So a phase line will not get the job done. I need a phase plane. So x-axis, y-axis. And then where is my equilibrium? At 2, 2. So at this point, I'm going to draw a big red dot to show equilibrium. But for example, like what happens at, let's just do like a couple of points by hand, and then we'll go to the internet, and I'll show you how Wolfram Alpha handles the thing. So what about the point x equals 1, y equals, actually, let's get off the nullcline. Let's do x and y both equal 1. If x equals 1, then what does that say about d? Oh, sorry, x equals 1, y equals 1. Then what does that say about dx dt? I get 1 times 1 minus 1 plus 1/2 times 1 times 1. So that first term vanishes and I get 1/2. And then dy dt will give me, so it should be the same exact value. So if dx dt is 1/2 and dy dt is 1/2, now keep in mind on a phase portrait, I'm not graphing, there's no time component in the phase plane. I'm graphing x versus y. So what I really want to look at is dy dx, which is going to be equal to dy dt over dx dt, which is going to be 1/2 over 1/2. So in this case, since the rates of change are identical, I'm going to have a rate of change of 1. So basically, I'm going to have, at this point here, a slope field, or a slope of 1. Let's do one more where the coordinates are different. Let's do x equals 4, y equals 3. X equals 4, y equals 3. What does that mean about my rates? dx dt is equal to 4 times 1 minus 4 plus a half times 4 times 3. So 4 times negative 3, that's negative 12 plus 6, negative 6. And then dy dt, that's going to be equal to 3 times 1 minus 3 plus a half times 4 times 3. So 3 times negative 2, that's negative 6 plus, oh, I think I landed myself on a null line. That's fine. So what did I learn here? dy dt is 0 and dx dt is a positive number. All right, so in this case, dy dx will be 0 over negative 6, so it'll be 0. So x equals 4, y equals 3. What's my slope going to look like? It's going to be a... And by the way, I should leave off these arrowheads because I'm graphing x versus y. There's no reason to assume that, you know, we're probably used to looking at graphs like this and assuming that it's going to be like y is going to be a function of x. So this thing's only going to march from left to right, which is not a safe assumption here in general. So did a couple of points just by hand just to kind of show like what's going to happen here. Now let me rely on Wolfram to run through this behavior quickly. So my equation number 1 is going to be 1 times 1, no, x times 1 minus x plus 0.5 xy. Equation 2 is going to be y times 1 minus y plus 0.5 xy. What interval do I want to look at? Let's try 0 to 10, 0 to 10, and see if that's okay. 0 to 10, 0 to 10, and we'll look at a phase plane. All right, so yeah, I mean, this is not reasonable for me to ask you what to do something like this by hand. But let's spot check the 3 values we know about. So what do we say at 2, 2? Can we see what's happening at 2, 2? It's hard to, I mean, you can't really, there's not like a big dot that says equilibrium, but if we kind of focus on 2, 2 here, like right around here, what we can see is that a bunch of arrows are like pointing in, which suggests to me heavily what kind of equilibrium point this is. I believe this is going to be a stable equilibrium because it looks like a lot of populations around this area are coming in. Like basically they're going to, the slope field is going to like push them towards 2, 2. Actually, as I look like a little more globally, it looks like that might happen from everywhere. Yeah, it looks like everything's kind of like filtering, you know, toward that value. Let's look at 1, 1. 1, 1 will be about here. We said it was going to be a slope of 1. That looks to be pretty faithful. And then let's look at our null lines. So our null lines, what does it mean for dx dt to be 0? That means that x is not changing with respect to time. If x is not changing, then we should have vertical lines because that's what it means for x not to change. So vertical lines, if we join vertical lines, you know, I see that happening up here, you know, and it kind of like, It's kind of hard to pluck out of here what exactly, what truly is vertical. So let's do this. Let's look at our graph. So for dx dt equals 0, that gave us the line y equals 2x minus 2. Okay, 2x minus 2. That means I have a y-intercept of minus 2 and a slope of 2. So basically, my y-intercept is not captured here, but that's okay. Where will this cross the x-axis? Should cross the x-axis at x equals 1. My slope is not drawn there, but the slope nearest to it is near vertical. But basically, if I were to follow a slope of 2 from here, basically the slopes that I cross should be vertical. And it looks like they're going to be not only vertical, but trending down. And I don't see any exactly vertical lines, but also I'm probably, the line that I am envisioning here is probably not crossing exactly the lines here that are drawn. So again, like, we can't make these vector fields infinitely dense, but I do see the behavior, like these very steep negative slopes that I would expect to see. What about the other null line? 1/2 x plus 1. So x equals 1 and a slope of 1/2. And I see the same sort of thing. I'm seeing, at this y-intercept here, the slope nearest to this is a little bit more positive than 0. But if I were to kind of follow up from there, and it's hard for me to see the horizontal behavior there. Do I need to recheck that null line? Let me see. X times 1 minus x plus 1/2 xy equals 0. Move that over. 1/2 xy equals negative x times 1 minus x. So 1/2 xy equals negative x plus x squared. Then I double everything. Xy equals 2x squared minus 2x. Y equals 2x squared minus 2x over x. 2x minus 2. I'm not even looking at the right one. So let me look at the right one. Y times 1 minus y, so that's y minus y squared, plus 1/2 xy equals 0. Doubling everything gives me 2y minus 2y squared, plus xy equals 0. Keep xy where it is, move everything else over. Xy equals 2y squared minus 2y. Then x equals 2y minus 2. But then if I solve that for y, what do I get? I'll get 2y equals x plus 2. So y equals 1/2 x plus 1. Yeah. Okay. Yeah, I trust that null line. I was just wondering why that's not showing up in my plot here. Or not that it's not showing up, but it's not like readily apparent to me. Maybe I'm following too sharp a slope. Let's do this. Let me pick a value of x that's further out. What if I say x equals 8? If x equals 8, then y will equal 5. X equals 8, y equals 5. Okay, that feels like it should be. That looks very roughly horizontal. Okay, so again, this phase portrait, I believe strongly is consistent with the null lines that I found, the few spot checks that I found. So this is the phase plane. Now what do I want to do? If the initial populations are given by x naught equals 2.4, so 2.4, 0.3. So here's what I'm going to do. I am going to turn on my zoom annotation tools and try to draw this. So initial condition of 2.4, 0.3. So 2.4 is about here. 0.3. There's 1, there's a half. Something like that. So initial condition right about there. So what does my solution trajectory look like if I start there? Basically what I'm doing is, you can metaphorically think of this phase portrait as currents. I'm going to essentially follow this current. And again, all I can really do is sketch. But what's going to happen here? Is this going to just keep going forever? No, not really. I think it's going to end right about there because, as we said, our 0.22 is, it looks like everything is kind of flowing into 2.2, or sorry, 22. So I believe my solution would more or less stop right there. All right, so I'm going to go ahead and clear my drawings, turn off annotation, and go back to PowerPoint. And we'll talk about question 2. So again, plotting phase portraits, we're probably going to go back to look at our look at Wolfram. So first, find the equilibrium points. I think the best way to find equilibrium points is to talk about the null lines. So because dealing with one equation at a time is simpler than dealing with both, then you can kind of find out where they intersect. So if dx dt equals 0, that means that cosine of y equals 0. So when is the cosine, for what angles is cosine equal to 0? If we look at the unit circle here, the cosine is essentially, if I have an angle that we'll call y, Technology is telling me to draw this larger. Got plenty of room. If this angle is y, then this point right here, or any point that you project with y, is going to be cosine of y, sine of y. Basically, the horizontal coordinate comes from cosine of the angle. The vertical coordinate comes from the sine of the angle, assuming that the radius of this circle is 1. So another way to reframe this question, for what angles is the horizontal component going to be 0? Well, that's going to happen at, let's just pick out a few and then we'll see if we can generalize it. It's going to happen at pi over 2. It's going to happen at 3 pi over 2. And then it's going to kind of repeat. So basically positive y-axis, negative y-axis. But then if I go around again, I'll have 5 pi over 2. And so essentially what I'm seeing is this. It's going to be pi over 2. And then every pi after that. So pi over 2 plus pi k, given that k is in this z, which is the integers. So as long as k is any integer, then that's essentially my null line, is this collection of values. If y is equal to pi over 2 plus any multiple of pi, essentially, any integer multiple of pi. What about the other null line? dy dt equals 0. Well, that means that negative x plus y equals 0. Or y equals x. So as long as y equals x, dy dt will be equal to 0. And dx dt will be equal to 0 as long as y. So this is a system that's only partially coupled. Or can I say that? No, I can't say that. because dx dt depends on y, dy dt depends on x, so it's fully coupled. But dx dt does not depend on x. Dx dt only depends on y. So the fact that it doesn't have that dependence means this. So I found my null clines. So equilibrium will be where these both are satisfied. So let's think about this. Let's draw a rough graph and see where these things kind of agree. I'm going to start with the dy, so the y null cline. The y null cline is this line. Y equals x. We understand what that line looks like, this 45-degree angle. So that's where dy dt will be equal to 0. Now, where will the other one also be satisfied? It's going to be satisfied wherever y is equal to a value that looks like this. So let's say this right here is the point pi over 2, pi over 2. I'll have equilibrium because the cosine of that y value is 0. But also negative pi over 2 plus pi over 2 is 0. I'll have, again, equilibrium at 3 pi over 2, 3 pi over 2. Or if you prefer, I can go backwards. Negative pi over 2, negative pi over 2. So it's weird to look at a straight line. It might be weird to look at a straight line and start plucking off values that you associate with trigonometry, but that's where I believe I have equilibrium. Another thing to point out, I graphed the full y null cline. That's what y equals x looks like. What do the x null clines look like? Well, it's anywhere where y equals these values. So let me delete these labels. Y equals a constant. What do those look like? Those always look like straight lines. So basically, my x null cline essentially is a collection of horizontal lines that are vertically spaced every pi over 2. And wherever these things meet, the y equals x line, my equilibrium is going to happen basically every so often, periodically along that line. So there's no way to like fully capture. Actually, that's not true. If my x null cline is captured this way, then I have equilibrium at these points. Pi over 2 plus pi k. Pi over 2 plus pi k. For k in the integers. And it's really important that I use k both places. I can't do pi over 2 plus 4 pi and pi over 2 plus 3 pi. XY coordinate has to be identical. So any place that meets that criteria, I'll have equilibrium. So that much I think is fair game to ask you to do by hand. Let's go back to Wolfram and look at the rest of this phase portrait. So this equation, x prime equals cosine y, y prime equals negative x plus y. This one kind of makes sense to look at negative values. So let's do this. Let's do negative 2. Do you like the number pi? Can I enter like that? Let's see. Let's do that on both scales and see what it looks like. Are you gonna get mad at me? Oh, you understood pi. Okay, so this is weird swirly thing. Okay. Does this make sense for us? I don't know. Let's talk about it. Where are our null clines? Well, I should have null clines so the horizontal lines are x null clines, which means at a bunch of different horizontal, like a bunch of different y values, I should just be crossing through vertical lines. So let's pick one out. Pi over 2 is 1, so that's about 1.5. If I cross through here, yeah, it looks like I'm just running through vertical lines. I mean, as far as you can tell, like, it's hard to tell what part of this arrow am I crossing through. The part where it starts to bend, because that'll be vertical. So again, these phase portraits, you cannot make them dense enough to see everything. So we kind of have to spot check what you want. Let's look at an equilibrium point. Does that make sense? We identified an equilibrium point as pi over 2, pi over 2. So where is that? So about 1.5, 1.5. That's about right here. I would say this is a deeply I was gonna say it's deeply unstable, but maybe not totally stable, because it looks like if you're coming from below and to the left, you're being filtered into this point. But other points, it looks kind of run away from it. So it looks like the stability depends very much on the heading you come from. In fact, it looks like if you're along the line y equals x, this might be stable. So this arrow is kind of pointing into it. This arrow is kind of pointing in. But if you're on, like, say, a perpendicular heading, that looks a little more clear that those are going to be like sources. Those are like filtering away. And then briefly describe the behavior of typical solutions. I'm not sure what would be typical here, but let's talk about a few things. It looks like for most, for at least for the field that I graphed, most of your solutions are going to trend either very high upward or depending on where you start. It looks like your y values are going to increase while your x values remain relatively stable. And what algebraically supports that? The fact that we have so many places where dy dt is positive, or dy dt is non-zero and dx dt is 0. Well, we found a ton of places where dx dt was equal to 0. There are infinitely many of them, and they always happen. They happen periodically. Whereas dy dt equals 0, also infinitely many places, but that happens in a more concentrated way. It happens on this y equals x line. So if I follow this y equals x line, and it's kind of hard to see them because it all depends on where these vectors are drawn, but anywhere along that y equals x line, you should have the dy dt equals 0, which means that you should have the horizontal lines. So I don't know if I can talk about a typical solution here, because the behavior is going to depend very heavily on where your solution begins. So let's go ahead and move on to question 3 or question 7. All right, let's go back to the slideshow. All right, so a lot of information here. So we're looking at the SIR model again. So how an epidemic moves through a community. So it moves from an isolated population. So people are not coming in and out of this area. Individuals are infected at a rate proportional to the product of the number of infected and susceptible individuals. So that part there is supported by this alpha SI. The length of the incubation period is negligible. Okay, so infectious individuals are immediately infectious. Okay, this thing spreads instantaneously. On the average, an infected individual dies after 10 days. This sounds extremely serious. Oh, they talk about Ebola. Only a single individual is initially ill. Okay. So tells us that, so that gives us an initial condition that I0 is 1. Oh, we're given that. All right. And then infected individuals do not give birth, but susceptible individuals have a birth rate of 0.0003 per individual per year. So that's supported here. Newborns are susceptible. Okay. The constant alpha is a measure of the relative infectivity of the disease. Some diseases, such as Ebola, are extremely infectious with a very high mortality rate. On the other hand, AIDS, which is caused by the HIV virus, has a much lower transmission rate. So both Ebola and AIDS are, well, not so much AIDS anymore. We've made a lot of advancements there, but there was a time where both of these diseases were, effectively, death sentences. Ebola, as far as I understand, still kind of is that way. But I think, yeah, that's kind of what this is meant to portray. So this model will be a good kind of but rough approximation for both of these, as long as we kind of tweak the constants, some of these parameters appropriately. If alpha equals 0.05, draw the phase portrait. Be sure to label all nullclines and equilibrium solutions. Let's do this. Let's, by hand, figure out where the nullclines and equilibria will be. Because I think picking them up from the Wolfram phase portrait is going to be a little bit cryptic, because like you just, it's kind of the luck of the draw where it draws your vectors. So let's do this. Where will ds dt be equal to 0? That's going to be essentially where 0.0003s equals alpha si. I'm going to go ahead and bring everything to the other side, which is the way I should have done it to begin with. Because both of these terms have an s, I can go ahead and factor that out. Minus alpha si equals 0. Factor out the s, and I get 0.0003 minus alpha I equals 0. So I have two equilibrium conditions implied here. One is where s equals 0, which is kind of the trivial equilibrium. If there's no one left who can be infected, then basically the population has been wiped out. So I mean, we'll go ahead and look at it, but we'll note it, but I don't think we're too interested mathematically in what happens there. The other one is going to be where essentially alpha I equals 0.0003, or if I solve for I get 0.0003 over alpha. So these are essentially my nullclines for ds dt, my s nullclines. So when s equals 0, ds dt will be equal to 0, or when I is equal to 0.0003 over alpha. I'm going to leave it as alpha for now, because that's the thing we're going to vary from part A to part B. What about when di dt equals 0? Then I also have this alpha si term minus 0.1 I. Did they explain where that 0.1 I came from? Oh, is it? Oh, because one individual dies every 10 days. Okay, that's why. All right. So if this equals 0, this time I'm going to factor out an I. So alpha s minus 0.1 equals 0. All right, so I equals 0, that is, I was going to say that's trivial equilibrium again, but it's not really that trivial, because if you have no infected people, then if you have no infected people and no one's moving in, so it's a closed population, then basically the disease has been eradicated for your little community. So that's a little more of a hopeful situation there. S equals 0 is very bleak. What does the other equilibrium look like? It looks like alpha S equals 0.1 or S equals 0.1 over alpha. So now I have my null clients for both, and they're pretty generalized, so I can kind of tailor these for when I start varying the value of A or alpha. Okay, and where's the equilibrium going to happen for both of these? They're kind of independent. So if S equals 0, well, then I obviously can't meet 0.1 over alpha. So over here in this margin, where will equilibrium happen? Equilibrium happens at S equals 0, I equals 0. So that's 1. Now I will say that's kind of the trivial one, because now that really does mean no one's left. No one's susceptible. No one is infected anymore. And then, based on this model, no one's recovering. So that's one null cline. The other one comes from, let me just make sure those are mutually exclusive. If S equals 0, S cannot equal 0.1 over alpha. If I equals 0, I cannot equal, okay, so yeah, that one of them is the 0, 0 case. The other one comes from S equals 0.1 over alpha, and I equals 0.0003 over alpha. So two equilibrium cases, and they're both, and the one of them is trivial. The other one is absolutely dependent upon alpha, which we said stood for basically is that how infectious the disease is? Yeah. Oh yeah, so that's right. So basically, the S times I is the number of interactions between people who are healthy and people who are sick. And then alpha is the proportion, basically the percentage of them, of those that will turn into infected. So if a susceptible person becomes infected, they are removed from the S group, and the I group gains them. All right, so I believe we've done all the analysis we can by hand before we have to go to, yeah, let's do this. Let's go back to Wolfram. And let's give Wolfram our new equations. So now I don't think I can give it a parameter, so I will go ahead and give it alpha. So negative 0.05 SI. I'll say that S is X and I is Y. So negative 0.05 XY plus 0.0003X. And then negative 0.05 XY. No, not negative. Positive. Minus 0.1 Y. What's a good interval? So it gives me an initial condition here. So let's start by saying that 1,000 people are susceptible and 1 person is sick. So my X scale is my susceptible variable. So let's go from, let's go 800 to 1,200. And then on the Y-axis, actually probably doesn't make sense for us. 0, 1,000, 0, 1,000. That might be a little too big, but let's see what happens. No, that's great. Okay, so what happens here? So very, very consistent behavior, but now let's talk about what this means. So remember again that X is the variable that stands for my um, the number of people who are susceptible, so the ones who are healthy but could be infected, and I, which is the vertical axis Y, those are my people who are getting infected. So let me turn on annotations again. Pretty much no matter what, no matter where I put a point in here, the behavior is going to be up to the left. So what does that mean about my situation? Well, it means that X is decreasing and Y is increasing. So my number of susceptible people is decreasing to 0, and my number of infected people will increase, it looks like, to 1,000. That's a little hard. Maybe it might be a little hard to argue because these are all, they look very linear. So let's do this. Let's tighten the axis on, let's tighten the x-axis to see what happens to the susceptible population. Let's go 0 to 200. No, that still seems to fit. It looks like no matter what, we're going to trend toward. Yeah, it looks like that behavior is roughly linear. Does that fit with our differential equation? It seems like it should. So in this case, with this, relatively high infection rate, 5%, 5% of interactions between people is going to end in infection. Basically everyone's going to get sick. So let's do this. Let me turn off let me clear my annotations. And we said we're going to find equilibrium conditions. Let's go ahead and find those specifically now. By annotations. So if S is equal to 0.05, 0.1 over 0.05, pretty sure that's just 2. Yeah, it's just 2. And then I will be equal to I got a number that doesn't make a ton of sense, because if I'm assuming that S and I represent numbers of people, this number isn't, yeah, it doesn't make a ton of sense. So this is for part A. What about part B? S equals 0.1 over 0.00. How many zeros? So 0.1 divided by 0.00001. S equals 100,000. And I equals 0.0003 divided by 0.00001, 300. So pretty different equilibrium conditions. This is part B. So even though it's the same equation, we're dialing in a parameter. Let's see what happens when I alter the equation and replot it. I'm going to go open up my axes again. Actually, I have a much higher initial population here. So I have 30,000, initially 30,000 susceptible individuals, only one infected. What do I got to change here? Instead of this parameter being 0.05, I'm going to change it to 0.00001. Okay, so new equation, new graph. So much different behavior. The last graph we were looking at looked like a bunch of parallel lines that were all trending left and upward. This one looks like it's trending left and they're not linear, they're trending down. So what does that mean in terms of our situation? So what does it mean for X what does it mean to go left on this graph? Well, that means that X is decreasing. X stands for the number of people who are susceptible. So that number of people is going down. So the number of people who are susceptible, that is decreasing. But what's happening to the number of infected? The number of infected is also going down. But I believe these rates are much smaller. I think that's why these arrows are much shorter than the last graph. So here's the bad news. I believe in both of these cases, so the last question we've got to answer is this. What's going to happen as time goes to infinity? I believe that in both populations, with no intervention, both populations are going to be eradicated. But when alpha is equal to 0.05, I believe that happens much more aggressively, much more quickly. The plot we just drew in part B, we had the same behavior. When I mean the same behavior, we still had the number of susceptible and infected people was decreasing, but it was not these rates, these slopes are shallower. One thing I want to do to be really, let's do an apples to apples comparison. Oh, that's those. Did I want to do 40,000 or 400,000? Let's do 40,000 on both. It didn't make sense for me to have them. I did not mean to have them both different scales. Okay, so now it looks a little more roughly linear. But what does the steep vertical downward slope means? Basically means that it looks like the number of susceptible people is decreasing. The number of infected people is decreasing. But which of those is more significant? It looks like, well, these are very vertical, much more vertical than they are horizontal. So I think the number of infected people is increasing at a much faster rate than the number of susceptible people. So maybe we should go back and look at what this looked like with our initial parameter. So 0.05, 0.05. And now we're going to squash these intervals again. So in this case, both of these phase portraits show, movement to the left. So the number of susceptible people is decreasing. But in this case, the number of infected people, they're universally increasing in this plot. Whereas for the lesser value of alpha, the number of infected people was decreasing. So again, I think the bad news is without intervention, both populations are going to go to zero in both of these cases. But the time in which it'll take to do that, that's going to be very different. C, what conclusions can you draw about the behavior of the two different epidemics? I think I've been kind of talking about that as we've been discussing this. Yeah, Similarly, both populations are going to go extinct. One is going to be much more slow. In part B, the number of infected people is going to change. It's going to decrease much more rapidly than the number of susceptible people. In part A, both were the number of infected people was increasing faster, basically at a rate faster than the infected people were. Sorry, I'll start over. The number of infected people was increasing at a rate more significant than the number of susceptible people was decreasing. That's why you saw those slopes that were going up to the left. And in part B, we saw trends that were going down to the left. All right, that's all for this section.